In the last video, we have calculated here the torque required to raise the load, that equal to P into dm by 2 is same as equal to W into tan of lambda plus pi multiplied by dm by 2. So if you expand here tan of lambda plus pi, you will get the expansion as tan lambda plus tan phi upon 1 tan lambda into tan phi. Here lambda is called as the lead angle. So we have TR is equal to W multiplied by the expansion of tan of lambda plus phi will be tan of lambda plus tan of phi divided by 1 minus tan of lambda into tan of phi. We know that the coefficient of friction is mu is nothing but tan of phi, where phi is called as friction angle, and tan lambda we can replace as pitch divided by pi into dm in the case of single start multiplied by dm by 2, which one is a mean radius at which the force will act. Now here tan lambda we can replace as pitch divided by pi dm because we have considered the single thread. Tan phi we can replace as coefficient of friction between the screw and the nut. So let's substitute here for tan lambda equal to P upon pi dm and tan phi is equal to mu. So this value of tan lambda we are replacing as P upon pi dm, tan phi we are replacing as mu upon 1 minus tan lambda is P upon pi dm, tan phi is equal to mu multiplied by dm divided by 2. Now pi dm and pi dm we can take as LCM in numerator and denominator. So we'll cross multiply and pi dm will get cancelled. So we have a simplified form of the equation of a torque to raise the load W into P plus V of mu multiplied by pi multiplied by dm is divided by, here pi dm will be cross multiplied to 1 will be pi multiplied by mean diameter dm, and here we left with mu multiplied by pitch P is further multiplied by mean diameter divided by 2. So either you can use equation 1 to find out the value of torque, or you can use the equation 2 if you know the value of pitch and the coefficient of friction, or otherwise you can calculate here lambda first using pitch upon pi dm and calculate the value of phi as tan inverse of mu and use the original equation 1. Choice is yours. Now we are interested to know what is the torque required to lower the end. This time the force applied in the exactly opposite direction. Because of this one, it will rotate in a clockwise direction. Because of a clockwise direction, the screw will approach towards the nut and the load will be moved downward. So again we have to develop the same figure that we have developed for the torque required to raise the load. As far as the direction of load is considered, this weight will act in a vertically downward direction. Then the normal force will be perpendicular to the plane. Lambda is called as the lead angle, pi dm is the circumference, and P is the pitch. So to lower the load, we are applying the force here P. So we can show the direction of force, that is the external force P. This time it is better to say PL. PL stands for the force required to lower the load. So this one is the direction of PL. Since here the load is moving downward, the friction force will act in a direction opposite to motion. So you have to show the friction force in a upward direction, that equal to mu multiplied by normal reaction N, where mu is a friction between the screw and the nut. So again you have to analyze this figure, this exactly opposite figure in terms of PL and mu N to raise the load. So when we are raising the load, we have shown the P upward. In that case, the load will move upward. Since the load is moving upward, the friction force will act in a direction opposite to motion. That is along the plane but in downward direction. So again, we have to carry out the same analysis. So when we raise the load, that time we get the equation for torque as W into tan of lambda plus phi into dm by 2. So analysis will skip here and we'll write the final equation of the torque required to lower the load. TL will be equal to W into tan of phi minus lambda multiplied by dm divided by 2. So when the load is moving in a downward direction, some component of the weight will use to overcome the friction, and the remaining friction is overcome by the external torque equal to TL. So therefore it is said here that the torque required to overcome a part of the friction in lowering the load. It is not a complete friction is overcome, because when the weight will move downward, naturally some component of the weight will use to overcome the friction, remaining is overcome by the external torque equal to TL. As far as when we have to move the load in upward direction, that time the entire torque is used to lift the load W plus additionally the friction between the screw and nut. But when you have to lower it downward, some friction force is overcome by the load W and the remaining friction force is overcome by the torque. That value of torque is given as W into tan of phi minus lambda into dm by 2. This value will be negative if the value of phi is greater than lambda. So if the friction angle phi is greater than the lead angle lambda, in that case TL will be negative value. And if the TL is negative value, it means that no external torque is required to lower the load. Now this is supposed to be a very dangerous situation in the case of screw jack. Suppose we are using a screw jack to lift the car. In that case, the car will be lifted, but as soon as you have to carry out the repair work under the car, and if the value of phi is greater than lambda, since no external torque is required, the value of P will be equal to 0. And since no force is required here to move the load downward, the entire car will move in a downward direction, and that may be a severe accident. And therefore always you have to take care that the value of TL must be positive. TL is positive only when the value of phi will be greater than lambda. This condition is called as self-locking. So if the value of phi, that is a friction angle, is less than the lead angle, then it is guaranteed always the value of TL will be positive. When the TL is positive, it means that the external torque is required to lower the load. That is the sum value of P you have to apply. So you must apply a certain force here that equal to PL. Then only the load will move downward. That is what we desired when we have to carry out the repairs under the car when we are using a screw jack. So if the value of phi is less than lambda, then TL is positive. We require here the external torque to lower the load. In such cases, the TL will be positive value, and whenever the torque is positive value, the given condition is called as self-locking. So this one is representing the condition for self-locking. As far as the screw jack is considered, we have to always design for self-locking. That is, you have to take the care that the value of phi should be less than lambda. The same concept of self-locking can be also explained on the basis of the circumference and the lead screw also. So we can expand here the term of tan of phi minus lambda. So we'll get here the torque required to lower down the load is equal to W into tan of phi minus tan of lambda divided by 1 plus tan of phi into tan of lambda, further multiplied by dm divided by 2. Now again we can replace here phi, that is tan phi is equal to mu and tan lambda equal to P upon pi dm. So if we substitute, we will get W into tan phi we can replace as mu minus tan lambda we can replace as pitch divided by pi dm divided by 1 plus tan phi is equal to mu and tan lambda is equal to pitch divided by pi dm, and again multiplied by dm divided by 2. Pi dm in numerator and denominator will get cancelled, so we have W pi into mu into dm minus the pitch P, and again divided by pi into dm plus we have mu into P, that is the coefficient of friction, multiplied by pitch, and again multiplied by dm divided by 2. So the value of the torque will be negative only if the value of pi into mu into dm minus pitch will be negative value. So for torque TL, if we want greater than 0, then we want pi into mu into dm should be greater than pitch, And for single start, pitch is same as equal to lead. So we have pi into mu into dm must be greater than the lead L. And this also represents the self-locking. So if the value of TL is positive, it is called as self-locking. And if we have the value of pi into mu into dm will be less than lead. That is, lead is greater than pi multiplied by mu multiplied by dm. In that case, no external force is required. So the value of PL will be equal to 0. And in that case, we'll get the value of TL will be negative value. So this may be possible in the case when we have very large lead. So you have to always use the lower value of lead in the case of screw jack, so that our value of TL is always positive value. So this one is the concept basically based on self-locking. So as far as the torque is considered, to lower the load, we have W into tan of phi minus lambda into dm by 2. And to raise the load, it is W into tan of phi plus lambda into dm by 2. To raise the load, we have W into tan of pi plus lambda into dm by 2. Up till now, our discussion is for square thread, and we have developed the two equations for the torque to raise the load and to lower the load. This time we are interested in the Acme thread, or for any thread profile that result in a slanted surface as shown in the figure. Previously the surface was horizontal, which one is a surface contact between the nut and screw. This time we have a slanted surface of contact between the nut and screw, which can be a case of Acme thread. So vertical load is always act in a vertically downward direction, that equal to W. The include angle here will be equal to 2 alpha. But for analysis, you have to always take the component perpendicular to the plane. So that component will be this component. So we have vertical component is same as equal to W. This angle is same as equal to the angle alpha. In that case, this component will be equal to W divided by cos alpha. That is, we have W into sec alpha. So this is the only change here. Previously we have the W component is coming alone. This time it is W into sec of alpha. So all this equation you have to modify by sec alpha. So for Acme thread, we have torque required to raise the load TR is given as W into dm divided by 2 multiplied by, we have pitch is equal to P, or we have lead is equal to L, one and same, plus we have mu into pi into dm. So additional term coming here is sec alpha, and is divided by pi into mean diameter dm minus mu into pitch. We have mu into pitch into sec of alpha. So this is a modification in the case of Acme thread. Similarly, we have torque required to lower the load is equal to W into dm divided by 2 into pi into mu into dm. So we have pi into mu into dm into sec alpha minus pitch divided by pi into dm plus we have mu into pitch into sec alpha. So this actually is most generalized equation. If you put the value of alpha will be equal to 0, it will become the square thread. In the square thread, the force is acting vertically downward on the horizontal plane. So you have to make the value of alpha equal to 0. If the value of alpha will be equal to 0, cos of alpha will be equal to 1, and therefore we have 1 upon cos alpha, which is same as equal to sec alpha, will be equal to 1. So this equation and this equation is one and same equation if we put the value of alpha equal to 0. One more friction we have to introduce, that is a collar friction. Suppose we are using a screw jack. So this one is the screw and we have stationary nut here, and if we have a load here equal to W. Since the nut is stationary, as you rotate the screw, the weight will also rotate. Whereas we desire here that the weight should not rotate. In that case, you have to use the collar. So if we use the collar, in that case, the screw is loaded axially. A thrust or collar bearing must be used between the rotating, that is the screw, and the stationary stage, that is the stationary member, in order to allow the screw to rotate without rotating the load. So we have here shown here one extra collar. Because of this collar provided here, and between the non-rotating stage and the collar, the friction will occur over the surface. That is, over this surface, the friction will occur. So this area we can represent as this area where we have a friction is occurring. Let R1 is the inner radius of the collar, R2 is the outer radius of the collar. Then the center line here represents the mean radius, and we have mean radius value is same as equal to R1 plus we have R2 divided by 2. So we can assume here that the load is acting exactly at the mean radius. So the load will acting at the mean radius Rm is vertically downward, and this one is perpendicular to the plane, so it will also called as a normal reaction. Since the collar is an integral part of a rotating screw, so collar will rotate also in the same direction. In that case, the friction force will act in a direction opposite to motion. So this one is representing the friction force. We know that the friction force is same as equal to mu. Here you have to use the value of mu c, where mu c represent the collar friction coefficient, and we have normal reaction is equal to same as W. So we have friction force additionally required is mu c multiplied by W. Here mu c represents the coefficient of friction between the collar and the non-rotating stage. We can call it as cup also. Now this value of Rm doesn't mean that the mean radius of the rotating screw. So I will modify this value. I will take this value as same as equal to Rc. Rc is the mean radius of collar. So in this case we require the additional torque to overcome the friction between the collar and the non-rotating stage. So here we can find out the torque required to overcome the friction at collar and the cup, that is the non-rotating stage. Let's call this one is equal to T2 value. This value is same as the friction force Ff multiplied by the mean radius of collar, that equal to Rc. But we have friction force is same as mu c, which is the coefficient of friction between the collar and non-rotating stage. So we have additional torque required equal to T2 is equal to mu c multiplied by normal reaction is same as equal to the load W multiplied by Rc, where Rc is the mean radius of collar. If you are familiar with the clutches, then this equation is basically designed on the basis of uniform wear theory. In the uniform wear theory, the mean radius Rm is always taken as R1 plus R2 divided by 2. So we have two torque required here. One is between the friction of rotating screw and the nut. So we have total torque will be equal to T1, that is equal to W into tan of phi plus lambda multiplied by dm by 2, plus we have additional torque is required. So this value is same as Tr plus additional torque required to overcome the friction is equal to T2. We can show this as a Tc also. So we use the symbol Tc, that is the torque required to overcome the friction at the collar. So we have total torque required to raise the load will be Tr plus we have Tc quantity. So final equation for torque is T is equal to W into dm divided by 2 into tan of phi plus lambda, where lambda is the lead angle, phi is the friction angle, plus we have the collar friction torque is equal to mu c multiplied by W multiplied by Rc. So we have developed the equation here for total torque required to raise the load, which is equal to W into dm by 2 into tan of phi plus lambda, plus we have collar friction coefficient mu c multiplied by load W multiplied by Rc. The unit of the torque is Newton meter, and normally we do not write radian, but actually the radian is always there. So this one is a torque exerted per unit radian. Suppose we make here one revolution, that is 360 degree or the total angle turn is equal to 2 pi, then theta will be the angular displacement equal to 360 degree is same as equal to 2 pi radian. So we can calculate here what is the input torque, that is T multiplied by theta. So here we introduce one more term that is called as the power screw efficiency. As we are familiar with the efficiency term, it is always defined as a useful work upon input work. Here we are keeping the load and the load will move vertically upward. In one rotation, the load will move vertically upward equal to the lead, and we are applying the torque is equal to T. For one rotation, we have theta is the angular displacement is equal to 2 pi. So we can calculate here the work, which is product of torque multiplied by theta. So we have input work is same as equal to T multiplied by theta. That is, we have T multiplied by 2 pi. So this one is Newton meter per radian, and the radian. Radian and radian cancel. We get a unit of Newton meter that equal to joules. So we have input torque is equal to 2 pi multiplied by T. Our calculation is based on one revolution, and in one revolution, the load will travel along the axis is equal to lead. So in this case, the actual distance traveled by the load W is same as equal to lead. So lead is same as our displacement. In that case, we can calculate useful work. Work is defined as the force multiplied by displacement multiplied by lead L. So we can put this value back here and we can calculate the efficiency. So we have efficiency formula in the case of power screw become useful work, which is W multiplied by L divided by input work is 2 pi multiplied by T. So remember this equation if you are interested to know what is the efficiency in the case of power screw. That is W into L divided by 2 times of pi multiplied by torque. The unit of W into L is Newton meter. Newton meter and Newton meter will get cancelled. This one is also Newton meter. So efficiency is a dimensionless term. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.